All right. Let's go through, and hopefully, like I said, you're not there yet. Hopefully, you will soon be there. But this is the string of sentences is off of this sheet. The order is slightly different, but if one of these statements is true, all of these statements are true. So it said acceleration is 0, which means your F net is 0, which means your velocity is constant, which means your forces are balanced. That's what I was hoping you were pulling from memory. Acceleration is 0, that means your F net is equal to 0, which means your velocity is constant, which means your forces are going to be balanced then. Now, it's up to you, I guess. But really, if you memorize one of these, then the opposite is true, right? So if your acceleration does not equal 0, then that means your F net does not equal 0. It's any non-zero number, which means your velocity is changing. Or that means it is accelerating, right? Which means your forces are unbalanced, yeah, unbalanced. Or you could say not balanced. I guess it doesn't really matter. They're not balanced or they're imbalanced. This is not balanced. Okay, so your worksheet called the worksheet that you had for homework was called Free Body Diagrams 2. And the intent of Free Body Diagrams 2 was really just to get you drawing these pictures as like a overall kind of start thinking about what forces. There's no calculations necessary. Today we're going to start adding values to these numbers. There was a question about, I don't remember which one it was, about the football moving through the air. A lot of times people have this idea that in order for an object to be moving, it must have a force acting on it. But I can take this bowling ball. Now I have to apply a force to get it moving. But once I push it, it's still moving the direction I push it, but I'm not actively pushing it anymore, right? So an object can keep moving without being actively pushed. You take a baseball, you throw it. Once it leaves my hand, I'm not pushing on it anymore. I'm not applying the force. If I kick a football, if I throw a football, once it leaves my hand or leaves my foot, why does it keep moving? Because you gave it some velocity. And it's called inertia, and it wants to keep moving, right? Newton's first law says object in motion is going to stay in motion. But once I throw that ball, because I'm not a Jedi, and I can't use the force to push it any further, there's no applied force on it anymore. Okay, so that's the kind of something to keep in mind. An object can move without being pushed down. So for this worksheet, we're going to draw free body diagrams, very similar to what I asked you to do for your homework, but now I want you to add magnitudes. And when I say magnitude, I mean I want you to put numbers next to it. And we want to include net force, and we want to add acceleration, if at all possible, which for these they are. The first couple problems are what we would refer to as equilibrium problems. But so if we have an astronaut with a mass of, if we have an astronaut that has a mass of 100 kilograms, is looking up at the night sky, dreaming about his upcoming mission to Mars, I should probably have added the word standing. Kind of a helpful word that will be good for us. So we want to draw free body diagrams. You are welcome to draw an amazing astronaut picture, whether they are in their spacesuit or not. That's completely up to you. Like I said, I'm not very good with drawing, but I do okay with boxes. So I'm going to pretend like that's my astronaut. The nice thing about drawing it as a box, and you say, well, that's not very nice, that person has feelings too, I know. I'm not saying that they are an object that has no feelings or emotions. It's just easier for me to draw. The nice thing about drawing a box is I can put I think it's kind of a nice little space holder for mass. You don't have to, I just think it's kind of a nice way. Because is mass a force? Mass is on the bottom of this sheet, is the amount of matter. So it's not a force, so it's not a force we're going to label in our free body diagram. Now by adding the word standing, hopefully we can kind of say, if he's standing there looking up at the night sky, we could then kind of probably, I think it's fair to draw the conclusion that his velocity would be constant, which then means his F net is 0, which means his acceleration is 0 and his forces are balanced. So because of that, we can say that his acceleration is 0 and his F net is also going to be 0, which means his forces are balanced. They're going to be balanced forces. So that's part of it, but what forces are actually acting on the astronaut?
Normal force and gravity.
Right, there's two forces, and there's the force of gravity going down, and because the forces are balanced, that means my ups have to equal my downs. So when I draw this normal force, that arrow should be about the same length. And the reason there's a normal force is there's a normal force anytime an object is sitting on a surface, and you say, well, he's standing. Yeah, he's standing, sitting, I'm going to call that the same thing. Okay? But now we want to put some values in. Of all 7 forces on our list, the 3 that I have highlighted have their own special equation associated with it. All 7 of these can be determined, given the right information, using Newton's second law. But these 3 that have their own equation, given the right information, you can use their own equation. Notice normal force is not highlighted. There's no special formula for it. However, f of g did have its own equation, and f of g is equal to m times g. It was listed right there. Force of gravity in the bottom of the sheet. Force of gravity is equal to the mass, and the mass is measured in kilograms, so that's our indicator that it's a mass, is 100 times the gravitational acceleration on Earth, because he's standing on Earth looking up at the night sky, and f of g is equal to 980 newtons. So then we can go over here and say that's 980 newtons. Now, if my forces are balanced and my F net is equal to 0, my ups minus my downs have to equal 0. What's my up have to be then? It has to be the same, right? It has to be 980. 980 newtons. Now, what we just did is we said the sum of all my forces is equal to F net, which is equal to mass times acceleration. We said our acceleration was 0, and we said our F net was equal to 0. According to this sheet, in the y direction, we add our ups, we subtract our downs. So I added my normal force, I subtracted my gravitational force, and they had to add up to 0. My normal force minus 980 is equal to 0. So therefore, my normal force is also going to be 980. That's where that came from. Why don't you try number 2? The same astronaut. Number 2 is the same astronaut. So the astronaut successfully made it to Mars and steps on a scale and is shocked by his weight because the gravitational acceleration on Mars is 3.71. Oh, actually, hang on, before you answer that one. When I ask you for weight, am I asking you for kilograms or am I asking you for newtons? Newtons. Because weight is also the same as force of gravity. And force of gravity is a force, and all forces are measured in newtons. So when I ask about the weight on Mars, I'm asking you to calculate the F of G of that same astronaut on Earth on Mars. Now, let's pretend. Let's pretend that his mass doesn't change on his journey. It's like in a 7-month journey, though, I think, or a 9-month journey to go from Earth to Mars. So the likelihood that his mass stays exactly the same in that 7 or 9 months, questionable, but we'll go with that. So why don't you try that one? So hopefully you recognize that he's standing on a scale, he steps onto a scale, so he's standing there, so therefore his acceleration is going to be 0, which means F net is going to be 0, which means his forces are going to be balanced. These are the two forces that are going to be acting on him, exact same two forces by name. Is his weight different? Does an astronaut's weight change when he goes to Mars? Yes. Does his force of gravity change when he goes to Mars? Yes. His F of G changes. Does his mass change when he goes to Mars? Does the amount of matter in that astronaut change when he went to Mars? No. He still has the same, we're going to pretend. He didn't lose any weight along the way, right? I'm sorry, I used the word weight. He didn't lose any atoms along the way. Now, he's got to eat. He's got to digest food. I get that. But if we talk about just if we could teleport him like right now, his mass would be the same. He has the same amount of atoms on Earth as he does on Mars. He's still going to be 100 kilograms, no matter where he is in the universe. His mass is going to stay the same. Does his F of G change, though? Does his weight change? Yes, because the gravitational pull is different. Therefore, the gravitational acceleration, the little g, is going to be different. Therefore, his F of G changes. So in this situation, F of G is still equal to 100 times, but now we're on Mars. The gravitational acceleration is 3.671. Therefore, this astronaut has a weight or a gravitational force of 371 newtons. And because my forces are balanced, when I add my ups, I subtract my downs, they have to add up to 0. This is also going to be, man. Mr. Finnegan, if you're watching this, you put these pens in the free box in the teacher lounge, and now I see why, because they don't work very long. I mean, thanks for the pen, Mr. Finnegan. That's what I meant to say. I'm sure Mr. Finnegan is just going to, on his spare time, stumble across Mr. Davies' physics YouTube video and watch today and find it. I'm sure. Maybe you want to draw his attention to today's lesson. Yeah. So, in this situation, the astronaut's mass stays the same. He still has the same amount of atoms. He's still 100 kilograms. Mass is independent upon the location. Not height. mass is independent of the location. However, the G is dependent of the location. So because my G changed, that stayed the same, the weight is gonna change that too. All right, let's take a look at number 3, a box. 5 kilogram box is sitting on a table. Sitting on a table. Why don't you try that one quick? If it's sitting on a table, is the velocity constant or changing? Constant, which means my forces are balanced or unbalanced. Which means my F net is 0 or not 0. Which means my acceleration, I think is the last thing, is 0. Okay, so that's what that says right there. And that's all because it was sitting on a table. These are the forces by name acting on an object. Because it's sitting on a surface, there's a normal force. Because my forces are balanced, these lengths of arrows should be about the same. What's the value that goes with them? What's the magnitude of these forces? 49, yeah. So how does that, well, we start with F of G. And F of G is M times G. And F of G is equal to 5 times 9.8. Grab the pen that Mr. Finnegan left me, times 9.8, and our F of G is equal then to 49 newtons. I mean, thank you, Mr. Finnegan. I appreciate the pen. So my F of G is equal to 49 newtons. Now, Newton's second law says you add up all your forces and you set equal to F net, which is equal to M times A, which we already said A was 0 and F net is 0. So add my ups, subtract my downs, they have to equal 0. So if my F net, my normal force is what we're solving for, we can say Fn minus 49 is equal to 0, and then because I'm lazy, I'm going to add 49 to the other side, and I'm just going to kind of make that minus an equal sign, and ta-da! So therefore, my normal force is also equal to 49. Not always. I'm going to say this, not always. But frequently, your normal force will equal your gravitational force. Because frequently, the only two forces acting in the y direction of an object is normal force and gravitational force. It's not always true. I can pick up on something without picking it up off the surface, right? There's a 300-pound chair. I can try really hard to lift it up. I'm applying a force up, but it's still sitting on the surface. So then that's a situation where your normal force is not equal to your gravitational. Because all of my ups, me applied, normal, minus all my downs, F of G, have to equal 0 in that case. These three are what we would call equilibrium problems, and the reason they're called an equilibrium problem is because they're called static equilibrium problems, I should clarify. My F net and my accelerations are equal to 0. Those are equal to 0. If it's not equal to 0, then it's not an equilibrium problem. All right, let's take a look at the fourth one. This is not an equilibrium. A 10 kilogram box is being pushed on a frictionless surface, which is caused to accelerate to the right at 3 meters per second squared. 10 kilogram box accelerates at 3 meters per second squared to the right. Okay, so what forces by name are acting on this object? Gravity,
Normal force,
normal force,
applied force,
gravity, normal, and which way is the applied force?
right,
Being applied to the right, and the reason we know it's applied to the right because it's being pushed, which causes a right word, causes it to accelerate to the right. It is being pushed, which causes it to accelerate to the right. And I can't push on something and make it accelerate in the opposite direction. Wait. No, okay. You know, I was, yeah. Trying to think, is there a way? Not, there's probably is an exception to that. But, so is this 0 or not 0? It's not 0, right? It is not 0, which means my F net is not 0, which means my velocity is changing, which means my forces are unbalanced. So what that tells me is there's going to be an F net, and my F net and acceleration always point in the same direction, which means my forces are unbalanced to the right. My forces to the right are bigger than my forces to the left. What's my value? What's the magnitude of Fg? 98, yep. Because Fg is equal to m times g. Fg is equal to 10 times 9.8. Fg is equal to 98 newtons. This is 98 newtons.
and probably the normal force is operating.
Because what's true about my forces overall? Are they balanced or unbalanced? Overall. They're unbalanced. Which direction are they unbalanced?
Right.
To the right, which then means my y direction, they are balanced, right? So because my normal force and gravitational force, those forces are balanced, this is equal to 98 newtons as well. Now we need to come up with this value, and we need to come up with this value. So the sum of all my forces is equal to F net, which is equal to mass times acceleration. That's Newton's second law. So if we want to solve for F net first, we want to kind of go that route. We can say F net is simply the mass, which is 10, times the acceleration. So my F net is 30 newtons to the right, is 30 newtons to the right. Now what that means is, this means my forces are 30 bigger to the right than they are to the left. So if I were to go with this option, where we're going to sum up all my forces, I can add my rights, I can subtract my lefts, there aren't any, and that has to add up to 30. So what does my applied force equal? My applied force is that 30 Newton force. My applied force is 30 newtons. I should almost box that in to kind of say, those aren't directly part of the free body diagram. The free body diagram is the forces. Questions so far? All right, why don't you try number 5 in terms of identifying the forces and determine the values. We'll go through the F net and the acceleration piece together, but why don't you try number 5? A ball, 1 kilogram ball is falling through the air. There is no air resistance pushing on it. So that's what your free body diagram should look like. That's it. There's gravity, and that's the only force acting. Now, if gravity is the only force acting on an object as it's moving through the air, what's the acceleration of that object going to be? Absolutely, negative 9.8 meters per second squared. Okay, now, I'll show you why. I don't want you to just blindly say, well, that's what it was in 1D motion. You're right, that is. But why is that the case? So, because there's no air resistance, so this is like the feather and the bowling ball in that vacuum chamber. Okay, this is not when there was air in it. This is no air. So while it was evacuated. When we go through and we say that sum of all my forces is equal to F net, which is equal to mass times acceleration, and if I say, well, I want to add up my forces, I'm going to add all of my ups, currently. I'm going to subtract all my downs, that's my F of G, and that's going to equal the mass of the object times the acceleration of the object. Now, right now, because this is a 1 kilogram object, you can say, hey, minus 9.8 is equal to 1 times A. I know that. But let's do a quick substitution. Because if we say F of G is equal to M times G, right, that's our formula. Mr. Finnegan, good thing I took 3 of these pens from the free bin. I mean, thank you, Mr. Finnegan. Thanks for the pen. If we were to say that's our formula, and if I were to do a substitution in there, so instead of writing it as Fg, if instead I wrote Fg as M times G, but remember, it's minus, right, there's that minus sign. And if we said that equal to mass times acceleration, what happens mathematically to our masses? They cancel out. Thanks, Mr. Finnegan, for walking by and yelling that. I appreciate it. So then, like Mr. Finnegan said, our acceleration is going to be, well, he didn't say that. He said our masses are going to cancel, so therefore our acceleration is going to be negative g, which g is on Earth 9.8. Does it matter if this is a 1 kilogram object or a 15,000 kilogram object? They cancel out, right? In the absence of air resistance, the acceleration of an object is negative g. So, to kind of wrap this one up, the acceleration is going to be down at negative 9.8 meters per second squared, and my F net is going to be down at 9.8 newtons. Now, I did not use arrows this time for the directions. I used negative signs, which is perfectly acceptable. When I draw my free body diagrams, all of those values are a positive magnitude, and I use the arrows accordingly there. But if I get a negative number, that tells me a direction. If I use a negative number, that tells me a direction. But I guess, well, maybe we should. Just to clarify that we're talking the y direction versus the x direction, we maybe should add 0 there, arrows too. Last one. 1 kilogram ball, once again, F of G, once again, is going to be 9.8 newtons. Why? Because F of G is M times G. This is 1, this is 9.8, this is 9.8. The difference is this time, we have air resistance. And in this situation, I tell you that the value or the magnitude of my air resistance is 5. Are my forces balanced or unbalanced? Which direction are they unbalanced? So is my acceleration 0 or not 0? Which direction is my acceleration going to be? Do I have an F net? Which direction is it going to be? Down. What's the value of that F net going to be? 4.8. right? So that's the idea here. The sum of all my forces is equal to F net, which is equal to mass times acceleration. If I add my ups and I subtract my downs, that's going to give me my F net. If I add my 5, I subtract my 9.8, that's going to give me my F net, and our F net is equal to negative 4.8 newtons. That tells me in the y direction that it's going to be moving down. My F net is equal to 4.8 newtons down. Oops, I drew that this way. Last piece is I want to go through and I want to determine the acceleration. F net is equal to mass times acceleration. If this is negative 4.8, this is 1, then hopefully very quick algebra will tell you that your acceleration is also going to be negative, which means down. .8 meters per second squared. Questions on those? Similar to yesterday's homework, except for now I'm asking you to put numbers in, putting values in to calculate some of these things. Now, this is kind of where we're heading, where we want to make sure we identify all of our forces, because we're going to need all of the forces in our upcoming problems. If you take that sheet and you turn it over, it says forces 1 on it. That's your virtual day assignment. So your virtual day assignment is kind of similar to what we just did, but it's not just saying draw a free body diagram and label everything. It's asking for some specifics. So if we take a look at like forces 1, which is on the back side of that worksheet, number 1. It says a force of 20 newtons accelerates an object to the right with a mass of 70 kilograms. Find the acceleration. That's what, and I did a very poor job of planning. There is a normal force. I hope you can see that. There's a normal force right there. These are the 3 forces I have. It's sitting on a surface, it's accelerating it to the right. Now, it should probably have a few more things. A 20 Newton force accelerates an object to the right while it's moving it across the surface, friction with the surface, something like that, whatever. This is my free body diagram. Now, what we just did is we went through and we came up with the magnitude of that and the magnitude of that. And you could, 70 times 9.8, because my forces are balanced in the y direction, my normal force and gravitational force are equal to, are gonna be the same. That's perfectly fine. But that's not what I'm asking for this. So if you want to, it's great practice, but that's not what number 1 is asking. It says, based upon this free body diagram, use that idea to determine what is my acceleration. So now what we're really doing is we're adding our rights, we're subtracting our lefts, we're setting it equal to F net, not really crucial. We're adding our rights, we're subtracting our lefts, and we're setting it equal to M times A, because I'm asking you to solve for the A. So you don't actually have to calculate this number and this number. It's good practice, not necessary yet. We will need that on, like, down the road a little bit when we start dealing with friction. Number 2 is similar, but now I'm giving you the acceleration, and I'm asking you to determine what that force is. So now, like this one, I gave you the applied force, I asked for the acceleration. Now I'm giving you the acceleration and asking for the applied force. And that's what I'm asking. Number 3 is just find the weight. When you get down to problems number 5 and number 6, I would encourage you to do number 6 before number 5. You do what you want. I think it might be helpful though. And when you get to number 5, number 5 talks about an astronaut who weighs. Remember, what is weight? Is that mass or is that force of gravity? Weight is force of gravity, gravitational force, right? So remember, I'm telling you the F and G. And if I tell you the effigy on Earth, I'm telling you how much he weighs. And now what happens is he's going to take a trip to another planet. So in order to determine his weight on the other planet, I'm asking you to solve what is his effigy on another planet. And I think by doing number 6 first should hopefully be helpful for you to do number 4. Okay. So with that, this is your virtual day assignment. It is posted in Canvas. It is as a PDF, also is its own PDF in the assignment. But if you have any questions on these, I would suggest you take a picture of it, email me. I can take a screenshot, I can write on it, I can send the feedback back. So that's my suggestion. We are pretty good, I think, in terms of time. So if you have any questions, please let me know. Otherwise, have a great weekend, everyone, and we will see you next week.